We are doing topic 3, gates and timing, and we started with simulation models and then transistors, and then we got into gates and timing actually, but then that's part 3.3. We talked about building gates, and what we did was we built an inverter, and with the inverter we I talked about the timing of it and so on and on. So we are building gates, but then with the inverter, because it was so simple, we could explain all the timings. We went in there, discuss all the timings, and now we are coming back up and say, well, okay, now we did inverter. Now let's do a few other gates. And with those other gates, we are not going to go into a lot of the details of the timing, meaning that since we already understand the inverter is it has a pull-up transistor, it has a single pull-down transistor, and it is very easily analyzable using basic current flow through the PMOS, through the NMOS. So we went into good depth understanding that, and then from this point on, we only focus on this structure. So let's talk about this NAND gate here, and let's say that the upper transistor or upper transistors have 8, 9, and 8, 7, and 9 delay. We have already discussed it. 8 is to 1, 7 is to 0, 9 is to Z. The lower transistors have 6, 7, 8, again to 1, to 0, to Z for the NMOS, and then for the PMOS is the upper one. So I'm not saying this is a NAND gate yet. Let's just say, well, this is a structure. The previous structure, instead of having the previous structure had only one pull up, one pull down. I say, well, now that I could put a one pull up, one pull down together and come up with an inverter, which was pretty good. So why not put two transistors at the lower side, which is the pull down, two transistors for the pull up. And so what we are doing now is we are trying to analyze this. Let's do this. A0, B0. Okay, A0, B0. If A is 0, B is 0, this one is open, this one is open, and the pull-up or the PMOS transistors, because they conduct when there is a 0 at their gate, this is conducting, this is conducting, and therefore by two paths I have from VDD to the output. This is the output W, and therefore I am getting a 0, a 0, I am getting a 1. Okay, now let's try a few other things. Let's say that A is 0 and B is 1. Okay, so I'm trying 0, 1. 0, 1, again, the A transistor is not conducting, but then the B transistor is conducting. Remember we said that we are talking about event-driven simulation. We are not talking about current flow. We are talking about NMOS transistor pushing a 0 to the output, PMOS transistor pushing a 1 to the output, and therefore a 1 on the B causes a push of 0 from the ground side of the NMOS of the lower NMOS transistor to the output side of it. But then when it reaches the A transistor, it's blocked. This is as far as the 0. The 0 is as far as it goes, is just go through this transistor, it just blocks there. And look at the upper ones. I have a 0, so I have again a conduction path, and I have a 1. I don't have a conduction path, but that doesn't matter because I already have a conduction path from the supply to my output, and therefore my output is going to be 1 anyway. I'm going to play the same thing with the other situation, which is 1, 0, and a 1 here, a 0 here. This is not conducting, this is conducting. But then what is it conducting? Look at the dark red. The lower transistor is not conducting, so it is, since it is not conducting, it is pushing a Z over to this point. And then the A transistor is conducting, but then that conduction is just taking Z. Remember, Z is nothing. It's taking the Z as putting it on the output. That means it's putting nothing on the output. Nothing on the output. That means the lower pass. Doesn't do anything to the output. Look at the upper path. The upper path, this is not conducting, but then this is conducting, and therefore, as you see, I have a 1, a 0, a 1. The last situation I want to look at is the 1, 1, 0. Okay, I have a 1 on A, a 1 on B, and then let's look at that. Let's not decide what it is. I have a 1 here, so this one is conducting. I have a 1 here, and therefore this is also conducting, meaning that the 0 that initiated from the B transistor, from ground, reaches the point between the two transistors and then goes up one level, or one transistor reaches the output. Okay, reaches the output, and therefore I have a 0 here. Okay, what is it? I have a 0 here, so I better have nothing from the top. If I have a something other than 0 coming from the top, I will get an X on my output. This is really, really bad. A 1 here is, this is not conducting, this is not conducting, and therefore good. I'm happy that the pull-up part, the two PMOS transistors, are not pushing anything to the output, and therefore my output remains 0. What do I have? What I have here is a gate structure that if the two inputs are 1, look, if A input is 1 and B input is 1, the output is 0. If A input was 1, B input was 1, the output was 1, I would have said this is an AND gate, an AND structure. But since when the two inputs are 1, the output is 0, I call this a NAND structure. Okay? This is a complementary logic. Look, either the structure at the bottom conducts or the structure at the top conducts. Either the pull down conducts or the pull up conducts. It is structured such that never, okay, they say never, it is unless, okay, let me say this. In stable situation, never the two parts conduct at the same time. In stable situation, never, none of the two conduct. Okay? That means either the pull-up or the pull-down conduct. Period. But I said in stable situations. There are transitional situations. There are situations that the pull-up is trying to push a 1, the pull down hasn't released the 0 yet. And therefore, you have a short period of time that both of them are conducting, or a short period of time that none of them are conducting, just like the inverter. So in transition, you get Z's and X's, but that's no problem. In a stable situation, You never have a situation that both of them conduct. And therefore, this is called CMOS, complementary MOS. Complementary means that the pull up and the pull down are always complementary. What did I say? I said this is a NAND gate. That means the output is 0 if both inputs are 1. See? Listen to this. If A input is 1 and B's input is 1, output is 0. Therefore, because output is 0, I put a bubble and call it a NAND. Let me read it a different way. The different way I'm reading it is this. If A is 0 or B is 0, see, if A is 0 here, or B is 0, okay, I'm not excluding 0, 0. If A is 0 or B is 0, or, of course, both of them are 0, the output is 1. Okay? I'm reading this gate in two different ways. The first way, which is if A is 1 and B is 1, the output is 0, is this symbol over here, which is an AND symbol. The second way I'm reading that same exact table. Okay? I'm reading the ones. I'm saying if A is 0 or B is 0, here. Okay? The output is 1, and therefore I don't put a bubble on the output, I put bubbles on the input. So this structure, this thing over here, it's either an OR gate with an OR function with inverted inputs, okay, for this case, for this case, for this case, for this case, or it is an AND function with inverted output. In either case, I call this an AND. It is an AND, even though it's drawn as the symbol with the OR inverted inputs. All right. Like I said, the upper part is called the pull up. The lower part is called the pull down. They are structurally complementary. That means the lower part, we have NMOS transistors. NMOS transistors conduct when the gate is 1. Upper part, we have PMOS transistors. They conduct when we have a 0 on the gate input. Okay, so transistors themselves are complementary. Structure is also complementary. Down below, I have 2 series transistors. Up there, I have 2 parallel transistors. And this stays with us forever, for as long as we are dealing with CMOS. Structurally, they are complementary. That structurally complementary, NMOS is always at the bottom, PMOS is always at the top, parallel serial. Okay? What we have in parallel below, we have serial up, or we have a combination as we will be showing. This situation always gives us complementary CMOS structures. And let's do the Verilog description for this. This is that same gate. This is the W output, and no different, not much difference between this and the other one. The inverter, I start with my NAND. I'm calling this my NAND. The A input, the B input, the W output. Okay, W output here. And okay, I have to write one transistor at a time. One transistor at a time. It doesn't matter which one I write first. The lower ones, the upper ones, however I want to arrange them, I can arrange them. Doesn't make a bit of difference if you write PMOSs first or NMOSs first. Okay, I'm emphasizing this because this description you see on the left hand side is a concurrent description. That means inside the module, you have a concurrent part. That means the statements or the order of the statements does not matter. All right. Let's look at the right hand side, and I want to write the first transistor. The first transistor here is supply 0. Supply 0. I'm happy with that. This is supply 1, by the way. Now, this transistor, the output of it is driven here, which connects to the input of the next one, up. Okay? I need a name. I need a wire. And therefore, I declared this node here as wire Y. Okay? So this is Y. Now, in the inverter, I didn't have something that was not named. Okay, in the inverter case, all the ports of transistors are either connected to the inputs or to the output. Here, I have, yes, a lot of them are connected to the inputs and the output, but then I also have another port here which is between two transistors, is not one of the inputs and outputs of the structure, and therefore I have to separately name it. Supply 0, supply 1 are the VDD and ground, and then I write my PMOSs or NMOSs. Okay? Like I said, this is concurrent, so if you want to put this NMOS here, you're welcome to do this. Okay, if you want to take this PMOS and write it all the way down below, you can do that, no problem. The same way, I don't tell you to twist this or turn this 90 degrees to the side. For as long as the namings is the same, for as long as the namings stay the same, this structure defines a NAND. And therefore, here the same way. For as long as the connections are defined properly, whether you write the PMOS or the NMOS first, it's not a procedural language. It's not a C programming. All right. Transistors. This is T1. This is T2. And T3 is the one ground. This is T3. This is T4. PMOSs 8, 7, 9. Just picked up 3 numbers. These are different than the NMOSs. They are larger than the NMOS delays, and therefore and they are larger than NMOS delays, and therefore the reason they are larger is because mobility of holes is larger than the mobility of electrons. And T1, okay, the input is let's start with the output. The output is W. Okay, see, the output is W, which is this. The input is VDD. The input is VDD. Okay, and the control, we call it the control, is A. This is A. Okay. Always the output is the one in the opposite direction of supply. The output is in the opposite direction of supply. Let's look at T4, for example. T4, the output is in the, let me do T3. I think T3 may be more interesting. the output is in the opposite direction of supply. Supply is down below, and therefore this is the output. And therefore, I put that first. What's the input? The input is the supply itself. Okay? The easy one is control, that comes last, and this one, control of this T3 transistor, is input B. All right. So this is the Verilog description of this, and I have also included, like I said, the delays, the transistors, the transistor names, this, or instance names. These are not mandatory. If you want to put them there, put them there. If you don't. The same way this drawing on the right hand side, if you don't put T1, T2, T3, nobody minds, as long as the interconnections are correct. Okay, but I do recommend that. So when you see circuit diagrams, they usually have the transistors, transistor names, or whatever component you put, they're there. And what I have up here is a very, very detailed description of the NAND structure. Okay? Very, very detailed description of the NAND structure. But then, and then it's good, actually, because these, when something changes, I see the Z's, I see the X's, I see all of these. But see, the problem with this description is that it has 1, 2, 3, 4 components. Okay? It has 4 components. When there is an event on A, 4 components see this. 4 components have to react to change on A. If I write my million transistor circuit like this, an event will cause many, many transistors to respond, to react, and therefore simulation time goes wild. I'm not talking about real time, simulation time. So I say, well, let's analyze this. Let's analyze this, and let's look at the timings. And once I'm happy with the timing, once I'm satisfied with the timing and I understand this, instead of having all these transistor delays, let's replace this whole description with a single NAND description. Okay, what I put here is NAND. That's the same description as above, except that there is a lot more details in the above than the below. So what I'm saying is I have a I have a NAND. Okay, I'm really looking at something like this. There is a W output, there is an input A, there is an input B, and then I'm saying to 1 delay is 16, to 0 delay is 14. 16, 14. Where did I get this from? Well, I analyzed the circuit on the above circuit. Maybe I put it in the simulation. Okay, but then the way I look at it is when I want to send the 0 through, the 0 has to go through this path. Okay? The 0 has to go through this path, and therefore I add the two zeros of the NMOS. The 2 zeros of the NMOS is 7. And therefore 2 0 is 14. 7 plus 7. Let's look at 2 1. 2 1. 2 1 is this. In order to send a 1 through, all I need is 8 nanoseconds from the top. But see, what I said was this. In order to be able to send the 1 to the output, to make the 1 appear on the output, you want to make sure that the two transistors below, they have given up. They have given up, meaning that they are sending Z's through. And therefore, you say, well, they can send Z's through 8 plus 8. That means B is disconnecting, sends a Z, sends it to point Y sends it to the T4 transistor, 8 plus 8 goes into W, W becomes Z, only then the output is a solid 1. Otherwise, the output after 8 nanoseconds pushes a 1, the lower input hasn't given up yet. The lower structure hasn't given up yet, and therefore for a period of 8 nanoseconds, that's if B is changing. For a period of 8 nanoseconds, you are getting an X on the output. And therefore, you put 16 for the 2-1 transition. You put the 14 for the 2-0 transition. What I just did was I analyzed the worst case delay of the circuit on the right hand side. I analyze the worst case delay of this circuit. What it means is that there may be situations that I don't have 16 nanoseconds. If A changes, I don't have 16 nanoseconds instead of B changing. But then that's not the worst case. If I want to replace this complex model, this is a complex model. If I want to replace this complex model by this little cute, simple model, what I do is I consider worst case delay so that I make sure that all the situations are covered. Both PMOS and NMOS, these are primitives. NAND is also primitive. Verilog gives it to me. But then Verilog says, if you really like to do detailed analysis, if you like to see your X's and your Z's and your things and all that, then do the upper simulation. If you don't care about the Z's and all that, if you have already analyzed your circuit, do the lower simulation. Actually, this is how it is. I have a complex gate. See, with the inverter, it was easy to analyze. With an AND, well, it was a little bit more difficult. Okay? Then I have a very complex case with a lot of transistors. Let's say with 6 transistors below, 6 transistors on top, that's 12. It's not that complex, but 12 transistors, if I want to go through all the Z's and the 1s and all that, that will be complex. So I have 12 transistors. I write this 12 transistor structure, which is not going to be NAND, it's not going to be NOR, it's going to be a complex structure. I write the transistors using the transistors, okay, with their delays and all that. Then I perform simulations. Maybe I have for that structure 3 inputs, 4 inputs. I will change all of those. And then I will eventually find that, okay, for this particular change, my output becomes worst case this situation, or my output becomes worst case for 1, worst case for 0. And then what I do, I replace that entire transistor structure with a very simple statement saying, okay, I have analyzed my transistor structure, I have found a worst case delay for the 1 and for 0. From this point on, I don't need to do that simulation, that slow simulation. I will put one little line describing my complex structure. And this is exactly what I have done here, except that this is not very, very complex. I could do that in a few minutes by just looking at the diagram. I encourage you to go in, type this in Verilog, and simulate it. And then you will be seeing the 16 and 14, I hope so, as the worst case delay for 1 and for 0. All right, what did we do? We did the NAND, and we are quite happy with that. And let's do another structure, this time a NOR. The NOR gate is not that different from the NAND gate, except whatever I had at the bottom, I had series transistors. On the top, I had parallel transistors. I'm going to switch. I'm going to put parallel NMOS transistors, series, and then parallel, and then pull-up transistors. They'll be in series. So this is my transistor structure for the what I'm calling NOR. Why do I call it NOR? You will know in a second. Okay. So I have this is my output, and this is A, this is B, and then let's look at the table. And now I'm going to do the same thing I did before. I have a 0, I have a 0 here, a 0 here. A 0 here doesn't conduct. Zero's up there. This conducts, this conducts. Okay, both of them conduct. That means I have a conduction path sending a 1 through to the output. Okay, let's do something else. This time, I'm going to have a 0 on A, a 1 on B. A 0 on A, a 1 on B. Still, this doesn't conduct. A 1 on B. This doesn't conduct, but this one sends a 0 through. Okay, let me draw it closer to the B transistor. Sends it through. What does it send? A 0 is sent. See, the supply 0 is sent, and therefore one path is enough to send a 0 through, and therefore the output is 0. Then I'm gonna do a 1 0, meaning that the A is 1 this time, B is 0, and let me go back to the previous one. I was trying to do it quickly. To the previous one, the 0 on A means that this is conducting, okay? But the 1 on B means that this is not conducting, and therefore the one that is initiated from VDD reaches this middle point between the two PMOS transistors, but it's not able to go to actually the one on the upper side of the B transistor doesn't reach the middle point, and therefore that lower transistor is not able to put a 1 to the output. Okay, there's two series transistors. Both of them have to conduct. If you want to put a 1, one of them is not conducting, so that's not going to happen. Let's look at the 1 0 situation, and actually this is basically the same. So a 1 meaning that this is pushing, a 0 through, a 0 is being there, and then this is not conducting. Let's look at the top. The top, because I have a 0, this is 0, and therefore this is conducting. Okay, but then this is conducting. Now this is happening what I was trying to say before. The supply reaches this point. But then the A transistor, because I have a 1 on its gate, is not conducting. The supply reaches this point, and this is as far as it goes, and therefore I only have a 0 in the output. And if both of them are 1, meaning a situation like this, a 1 here, a 1 here, it means that I push a 0 through here, I push a 0 through here. None of the two transistors on top are conducting. A 1, a 0. And therefore I get a 0 and then another 1. Let's read this. Let's read the table here. I have a circuit that when I'm going to draw that when both inputs are, or when let me do this. Yes, I have a circuit on top when A input is 0. Okay, A input is 0, and B input is 0, okay, the output is 1. I'm going to draw it differently. I'm going to draw it. I have a circuit that if A is 1 or B is 1, A is 1 or B is 1, the output is 0. Okay, both of them tell me this is a NOR gate. But NOR comes from here, complementing the OR output. Therefore, these are the two representations for NOR, and either an OR with a bubble output or AND with bubble inputs. I don't go through the timing, and for Verilog description, you can do exactly the same. And for Verilog description, you have a primitive NOR that you can use, very similar to the AND primitive that we had over here. Okay. All right. What we do next is complex gates. We do this in the next